Google AI releases MLE-STAR, a machine learning engineering agent capable of automating various AI tasks. On August 2, 2025, Google AI unveiled MLE-STAR machine learning engineering via Search and Targeted Refinement, a groundbreaking machine learning engineering agent that has demonstrated a remarkable ability to automate various AI tasks. This new agent achieved an impressive 63.6% medal winning rate on Kaggle's MLE-Bench-Lite benchmark, significantly outperforming both previous autonomous ML agents and human baseline methods. The pain points before MLE-STAR. Prior to the advent of MLE-STAR, the process of building robust machine learning models was fraught with difficulties. Practitioners often found themselves scrolling through outdated Kaggle notebooks attempting to guess which feature engineering tricks were effective and rewriting entire scripts after each unsuccessful run. Existing automated agents typically followed a similar pattern, relying heavily on generic libraries such as scikit-learn, which resulted in shallow pipelines and slow progress. This traditional trial-and-error approach was inefficient, leading to frustration among data scientists and engineers. Key innovations of MLE-STAR. MLE-STAR's development is anchored in several key innovations that address the limitations of previous methodologies. 1. Web search-driven model selection. MLE-STAR utilizes web searches to gather the most recent models and code snippets relevant to specific tasks. Unlike prior agents that relied on pre-existing knowledge, MLE-STAR starts with a fresh perspective, incorporating up-to-date practices and avoiding the pitfalls of outdated architectures like ResNet. For instance, when tackling image-related tasks, MLE-STAR may begin with advanced models such as EfficientNet or Vision Transformers VIT. 2. Targeted code refinement. The agent implements a dual-loop refinement process. Outer-loop ablation studies. MLE-STAR systematically tests the impact of individual components of the machine learning pipeline to identify which aspect most significantly affects performance. Inner-loop focused exploration. Once a critical component is identified, MLE-STAR generates and tests variations of that specific code block, enabling precise improvements rather than broad modifications. This targeted approach ensures that changes lead to meaningful enhancements. 3. Self-improving ensemble strategies. MLE-STAR employs advanced ensemble methods that combine multiple candidate solutions rather than merely averaging results. This innovative strategy leverages the strengths of individual models, resulting in a more robust final output. 4. Robustness and safety checks. The agent integrates specialized components to enhance the reliability of its operations. Debugging agent automatically identifies and corrects errors in the code until it runs successfully. Data leakage checker inspects the code to prevent information from test or validation samples from biasing the training process. Data usage checker ensures that all provided data files are utilized, improving model performance and generalizability. Performance metrics. MLE-STAR's performance on 32 Kaggle tasks demonstrates its superiority in the field. Medal rate achieved a 63.6% any medal rate and a 36.4% gold medal rate, compared to only 25.8% for the best baseline method. Above median submission rate, 83.3%, indicating that the majority of its submissions rank higher than the median performance. Valid submission rate, 100%. Illustrating its reliability in generating operational scripts. These metrics highlight MLE-STAR's effectiveness and efficiency in automating the machine learning engineering process. Addressing existing limitations. Before MLE-STAR, the process of developing effective machine learning models involved tedious trial-and-error methods reliant on previous knowledge and generic libraries. Existing agents often failed to probe deeply into the code, leading to inefficient pipelines and slow progress. MLE-STAR directly addresses these issues by combining web-driven insights with targeted refinements, resulting in a more streamlined and effective approach to machine learning engineering. Conclusion and future implications. The release of MLE-STAR marks a significant leap in the automation of machine learning engineering. By integrating web search's targeted refinements and robust safety checks, it not only outperforms previous autonomous agents but also sets a new standard for future developments in the field. The open-source nature of MLE-STAR allows researchers and practitioners to adopt and extend its capabilities, fostering innovation and productivity within the machine learning community. As this technology continues to evolve, MLE-STAR has the potential to redefine workflows in machine learning engineering, enhancing accuracy and efficiency across a wide array of AI applications. The implications of its success could lead to more advanced and automated solutions, ultimately pushing the boundaries of what is possible in the realm of artificial intelligence. Sources and references. MarkTech post, detailed insights into MLE-STAR's core innovations and performance metrics. Twitter and Facebook, concise overviews emphasizing the impact of MLE-STAR on the machine learning engineering landscape. Google Research, official publication and technical details regarding MLE-STAR and its capabilities. For further reading, the full technical paper GitHub repository and additional tutorials are available through Google's official channels, encouraging collaboration and exploration within the AI research community. The release of Google AI's MLE-STAR introduces a machine learning engineering agent that embodies several counterintuitive features and approaches to automating machine learning tasks. Here are some of the notable counterintuitive aspects of MLE-STAR's design and functionality. 1. Web search as a foundational tool. Traditionally, machine learning models have relied on pre-existing datasets and established libraries such as scikit-learn. However, MLE-STAR begins its process with web searches to gather the latest code snippets and research papers. This approach is counterintuitive because it deviates from the norm of relying solely on internal knowledge or pre-existing frameworks. By tapping into current information from the web, MLE-STAR can access state-of-the-art models like EfficientNet or VIT, which may not be part of the standard libraries used by most existing agents. 2. Targeted code refinement instead of broad changes. Previous machine learning agents often employed a trial-and-error approach that involved rewriting entire scripts when faced with failure. MLE-STAR conversely utilizes a dual-loop refinement process that allows for focused exploration of specific components of the code. After identifying which part of the pipeline affects performance the most via ablation studies, it hones in on that specific section, creating and testing variations. This targeted approach contradicts the common practice of making sweeping changes in hopes of improvement, offering instead a methodical way to enhance model performance. 3. Self-improving ensemble strategies. MLE-STAR takes a unique stance on ensemble methods. Rather than simply averaging the results of different models or selecting the best performing one, it employs an adaptive ensembling strategy that tests various ensemble configurations and seeks to blend the strengths of different models. This approach is counterintuitive because it challenges the notion that ensembling is merely about aggregating results. Instead, MLE-STAR actively seeks to refine the ensemble strategy based on performance feedback, leading to more robust outcomes. For robustness through specialized agents, MLE-STAR incorporates microagents dedicated to specific tasks such as debugging and preventing data leakage, which is a departure from the singular focus on model training. The idea that validation and error checking should happen within the same framework as model development may seem counterintuitive, as many practitioners view these as separate concerns. However, by integrating these safety nets directly into the workflow, MLE-STAR enhances reliability and improves overall model performance. 5. Emphasis on continuous learning and adaptation. MLE-STAR's design allows for continuous refinement and adaptation, which runs counter to the more static nature of traditional machine learning models. The agent is not simply a one-time solution. It learns from each iteration, adjusting its strategies based on what has been successful or unsuccessful. This dynamic approach challenges the conventional perception that machine learning models are finalized after initial training and testing. 6. High performance despite generic prompts. the performance of MLE-STAR achieving 63.6% mental wins on Kaggle tasks is particularly striking because it does so using generic prompts and automated loops rather than handcrafted features or bespoke tuning. This outcome defies the expectation that superior performance in machine learning requires meticulous manual crafting of features and tuning parameters. The agent's ability to produce high-quality results through automation and web-sourced ideas suggests a paradigm shift in how machine learning tasks can be approached. 7. 100% valid submission rate. Another counterintuitive aspect is the 100% valid submission rate achieved by MLE-STAR. This metric implies that every script generated by the agent was operational, which runs counter to the common experience where generated code often requires significant debugging and adjustment. This reliability challenged the assumption that automated code generation inherently leads to higher error rates. 8. Inclusion of human feedback. MLE-STAR allows for human experts to inject information about new models directly into the system. This collaborative feature is counterintuitive as it suggests that even advanced automated systems can benefit from human expertise. The expectation is often that fully automated systems would minimize human intervention, but MLE-STAR demonstrates that integrating human insights can enhance its adaptability and performance. In summary, MLE-STAR's innovative strategies challenge traditional machine learning paradigms, offering insights into automation, refinement, and collaboration that may reshape the landscape of machine learning engineering. Its reliance on current web resources, targeted refinement, self-improvement strategies, and integration of safety measures provides a fresh perspective on achieving high performance in machine learning tasks. The release of Google AI's MLE-STAR represents a significant advancement in the field of machine learning engineering, particularly in automating the development and optimization of machine learning ML models. While the report highlights various innovations and performance metrics, there are several critical elements that many readers may overlook which are significant for understanding the broader impact and potential applications of MLE-STAR. 1. Web-driven model selection. One of the standout features of MLE-STAR is its use of web searches to gather the latest code and model architectures. This approach allows it to stay current with advancements in the field, avoiding the pitfall of relying on outdated models. The significance of this innovation lies not just in its immediate performance improvements but in how it fundamentally alters the workflow of ML engineering. Traditional methods often involve tedious searches through historical notebooks and libraries that may not reflect the latest best practices. By leveraging web resources, MLE-STAR democratizes access to cutting-edge techniques, enabling practitioners to utilize state-of-the-art methods without extensive manual research. This can lead to faster adoption of new technologies and methodologies, ultimately driving innovation in ML projects. 2. Targeted code refinement process. The dual-loop refinement process employed by MLE-STAR is another area that deserves attention. The outer loop focuses on ablation studies to identify which component of the ML pipeline is most impactful, while the inner loop hones in on that specific component for targeted improvements. This method is significant because it showcases a shift from traditional trial and error approaches to a more systematic and scientific method of optimization. Rather than making broad changes that could disrupt the entire model, MLE-STAR's approach allows for surgical modifications which can lead to quicker iterations and improved model performance. This can save researchers significant time and resources, reshaping how ML models are developed and tested. 3. Self-improving ensemble strategies. MLE-STAR's self-improving ensemble strategies are another key feature that may be underappreciated. Instead of simply averaging the outputs of multiple models, MLE-STAR intelligently combines them using advanced techniques. This could imply a significant leap in ensemble learning strategies within ML, as it demonstrates the potential for learning from multiple models in a way that enhances overall performance. The implications are vast. If MLE-STAR can refine the way models are combined, it could lead to breakthroughs in achieving higher accuracy in predictions across a variety of tasks and datasets. This flexibility in model management might inspire future research directions focused on adaptive ensemble methods. 4. Robustness and safety checks. The integration of specialized agents for debugging data leakage prevention and ensuring comprehensive data usage is an aspect of MLE-STAR that should not be overlooked. These safety checks enhance the reliability of the outputs generated by the agent, which is crucial in real-world applications where model robustness is a primary concern. This level of rigor in error handling and data management could serve as a benchmark for future ML automation tools, emphasizing the importance of reliability and trustworthiness in AI solutions. By preventing common pitfalls such as data leakage and overlooking critical data, MLE-STAR sets a precedent for responsible AI development. 5. Open source development and community engagement. MLE-STAR's open source nature is a critical detail that can have far-reaching consequences. By allowing researchers and practitioners to access and modify the agent, Google AI fosters a collaborative environment for innovation. This openness not only accelerates the dissemination of knowledge but also encourages community engagement in refining and enhancing MLE-STAR's capabilities. The significance of this aspect lies in its potential to create a thriving ecosystem of developers who can contribute to and evolve the tool, ultimately leading to more rapid advancements in the field of machine learning engineering. 6. Practical implications for professionals. For professionals in the field, MLE-STAR could significantly alter workflows. The ability to automate the more tedious aspects of model development, like feature engineering and hyperparameter tuning, allows data scientists to focus on higher-level strategic tasks. This shift in focus could lead to more innovative solutions and applications of machine learning as practitioners find themselves with more time to explore novel research questions and applications. The efficiency gained through MLE-STAR's capabilities may also reduce the entry barrier for those new to machine learning, democratizing access to sophisticated modeling techniques. 7. Future directions for machine learning engineering. MLE-STAR's advancements suggest potential future directions for the field. The emphasis on web-driven model selection and targeted refinement could inspire the development of new frameworks and tools that incorporate similar principles. This might lead to an evolution in how machine learning frameworks are structured, with a greater emphasis on modularity and adaptability. As more organizations adopt tools like MLE-STAR, we may also see shifts in best practices within the industry, pushing for more collaborative and open approaches to machine learning development. Conclusion. In summary, while the report on MLE-STAR outlines its impressive performance metrics and technical innovations, the underlying implications of these advancements are equally, if not more, important. The emphasis on web-driven insights, targeted refinements, ensemble strategies, and robust error handling showcases a significant leap forward in machine learning engineering. Moreover, the open-source nature of MLE-STAR invites community engagement and collaboration, potentially reshaping the landscape of ML development. Understanding these nuances not only highlights MLE-STAR's role in the present but also its potential to influence future trends in machine learning. Here are the 4 most valuable points for in-depth analysis and discussion regarding Google's MLE-STAR. 1. Web search-driven model selection. MLE-STAR distinguishes itself by using web searches to gather contemporary models and code snippets relevant to specific tasks. This approach contrasts sharply with previous agents that relied on outdated internal knowledge, often sticking to default libraries like scikit-learn. By pulling in the latest methodologies and architectures, e.g. efficient NetVit, MLE-STAR ensures that its initial solutions are based on cutting-edge practices. This innovation not only enhances its effectiveness in specific tasks but also accelerates the adoption of state-of-the-art techniques in machine learning engineering. 2. Targeted code refinement. The dual-loop refinement process in MLE-STAR is noteworthy. The outer loop conducts ablation studies to pinpoint which components of the ML pipeline significantly influence performance, while the inner loop focuses on generating and testing variations of the identified critical code block. This targeted approach allows for precise improvements, avoiding the inefficiency of broad script rewrites. By isolating the components that matter most, MLE-STAR can systematically enhance the performance of its models, thereby reducing trial-and-error inefficiencies that have plagued previous ML engineering efforts. 3. Self-improving ensemble strategies. MLE-STAR employs advanced ensemble methods that go beyond simply averaging results. Instead of just selecting the best performing model, it explores intelligent combinations of multiple candidate solutions. This includes strategies like stacking and optimizing weights, which can lead to superior performance. The self-improving nature of its ensemble strategies positions MLE-STAR as a powerful tool in machine learning capable of leveraging the strengths of individual models to create a more robust final output. This aspect raises discussions about the future of ensemble learning in automated ML systems. 4. Robustness and safety checks. MLE-STAR integrates specialized agents that enhance the reliability of its outputs by automating essential safety checks. These include debugging agents to catch and correct errors, data leakage checkers to ensure the integrity of training processes, and data usage checkers to maximize the utilization of all provided datasets. This level of rigor in maintaining the quality of generated scripts represents a significant leap forward in ML automation, addressing common pitfalls associated with automated code generation. The implications of such robust safety mechanisms are profound, as they can pave the way for broader adoption of AI in critical applications where reliability is paramount. Each of these points not only highlights the innovative aspects of MLE-STAR but also opens avenues for further exploration and discussion regarding the future of automated machine learning engineering. 1. IBM Watson's victory on Jeopardy! 2011, IBM Watson, a computer system designed to answer questions posed in natural language, competed against two of the best human players on the popular quiz show Jeopardy! In 2011. Watson's ability to parse complex questions and quickly retrieve information from a vast database allowed it to win against its human counterparts, showcasing the potential of AI in understanding and processing language. The match highlighted the advancements in natural language processing and machine learning, marking a significant milestone in AI history. 2. DeepMind's AlphaGo defeats Lee Sedol. 2016, AlphaGo, a computer program developed by DeepMind, made headlines when it defeated Lee Sedol, one of the world's top Go players, in a 5-game match in 2016. This event was particularly significant due to the complex nature of the game, which has an enormous number of possible moves and strategies. AlphaGo's victory demonstrated the advanced capabilities of reinforcement learning and deep neural networks, marking a pivotal moment in AI development and the application of machine learning techniques to complex decision-making tasks. 3. The development of autonomous vehicles. 2010's present. The evolution of autonomous vehicles, particularly those developed by companies like Waymo and Tesla, represents a significant application of machine learning and artificial intelligence. These vehicles use deep learning algorithms to interpret sensory data, make driving decisions, and navigate safely through various conditions. The ongoing advancements in this field have the potential to revolutionize transportation and urban planning, as well as raise important discussions on safety, ethics, and regulation in AI technology. Future outlook for MLE-STAR and machine learning engineering. The release of Google's MLE-STAR represents a significant evolution in machine learning ML engineering, promising to reshape workflows across various sectors. As we project into the future, several key trends and predictions emerge regarding the impact and evolution of MLE-STAR and similar technologies. 1. Increased automation in ML workflows. As MLE-STAR automates various AI tasks with remarkable efficiency, we expect to see a broader trend toward automation within ML pipelines. This shift will not only streamline the development process but also reduce the reliance on human intervention in routine tasks. By 2030, many organizations may adopt fully automated ML solutions for tasks such as data pre-processing, feature selection, and model evaluation, freeing data scientists to focus on more strategic initiatives. 2. enhanced collaboration between humans and machines. The human-in-the-loop approach that MLE-STAR supports will likely gain traction. As experts can provide insights into new model architectures or domain-specific knowledge, we foresee a collaborative environment where human intuition and machine efficiency coalesce. This partnership will leverage the strengths of both parties, leading to innovative solutions that are both robust and contextually relevant. 3. Continuous learning and adaptation. MLE-STAR's ability to integrate the latest models and techniques from web searches signifies a shift toward continuous learning in ML agents. In the coming years, we anticipate that ML systems will evolve to not only source information from the web but also learn from their interactions and experiences. This capability will enhance their adaptability, allowing them to refine their approaches based on real-time feedback and emerging trends. 4. Democratization of machine learning. With MLE-STAR's open-source nature, we expect a democratization of machine learning capabilities. Small businesses and individual developers will have access to state-of-the-art tools that were previously the domain of large tech companies. This accessibility will spur innovation across various sectors as diverse players will contribute to and expand upon existing frameworks, leading to a richer ecosystem of solutions. 5. More robust ML solutions through advanced safety mechanisms. As automation in ML engineering increases, so will the necessity for robust safety measures. MLE-STAR's specialized agents that check for data leakage and debugging will set a precedent for future systems. By 2030, we predict that all major ML platforms will incorporate advanced safety protocols to ensure the reliability and integrity of automated processes, thus mitigating risks associated with model deployment. 6. Expansion beyond traditional ML tasks. MLE-STAR's success in various Kaggle competitions indicates its versatility, but we expect its application to expand further into uncharted territories. Future iterations of ML agents will likely tackle more complex tasks across sectors such as healthcare, finance, and autonomous systems. By integrating domain-specific knowledge, these agents will optimize processes that require nuanced understanding and specialized skills. 7. Evolution of evaluation metrics. The performance metrics established by MLE-STAR will catalyze a re-evaluation of how we measure the success of ML models. As automation becomes prevalent, traditional metrics may evolve to include efficiency, speed of iteration, and the ability to learn from failure. By emphasizing these new criteria, organizations will better align their ML efforts with strategic business outcomes. 8. Integration with broader AI ecosystems. MLE-STAR's foundational design within Google's Agent Development Kit (ADK) suggests a future where ML agents seamlessly integrate into larger AI ecosystems. We envision a landscape where different AI agents, each specializing in distinct tasks, collaborate to achieve common objectives. This interconnectedness will enhance the overall efficacy of AI applications, fostering comprehensive solutions that address complex problems. Conclusion. As we look ahead, MLE-STAR and its successors are poised to revolutionize machine learning engineering. By facilitating the automation of tasks, enhancing collaboration between humans and machines, and promoting the democratization of AI tools, the future of ML appears both promising and transformative. Organizations that embrace these advancements will not only improve their operational efficiencies but also unlock new avenues for innovation, setting the stage for a future where AI becomes an integral part of everyday problem solving.